Hey everybody, today I have a really cool video for you guys. Basically, we're going to be taking points on a circle, just any points on the circle, and we're going to be mapping them to the boundary of the sphere. So the boundary is just the outside, so no points are going to be going on the inside of the sphere, just the boundary of it, okay? And that's, you'll see why soon. Okay, so basically what that means is, let's say we have 2 points, let's say C1, and then C2, right? And they're going to have a distance, let me put C2 over here. They're going to have a distance, I'm going to call that L, from each other. And so they're going to map, and they're going to be in the same kind of position relative to each other. The condition with the mapping is that they are in a uniform distance from each other, okay? So I'm not working with any of the technicalities here. I wouldn't really know like what side it gets mapped on, whether it gets mapped on, this side of the sphere or the back side. I guess just for the purposes of this, C1 and C2 get mapped to the front of the sphere, just for simplicity, all right? And so they're going to be mapped to some point, and it's going to look weird to draw it on 3D space, but I'm going to try. So let's say f of C1 is here, and then let's say f of C2 is over here, and they're both on the front again, so let me put f of C2 there, and it's going to look kind of like some curvature there. I don't think I drew that well, but it's good enough. So basically they're going to have this distance L, and they're going to have a proportional distance along that curve, because that distance L is not going to really be proportional like directly. You have to go kind of along the boundary, because that's what our domain is. So here, I'm sorry, our codomain. So the domain is the circle, and the codomain is the boundary. So the inside of the sphere doesn't really exist in our point of view, so you can't actually cross it. We're going to travel along, and it's really not hard to see what that proportionality constant is, because if you consider the area of the circle, the area of the circle, so I'm going to label that with a capital C subscript, the area of the circle is just pi r squared, okay, where r is the radius of the circle, and I don't know if I mentioned, but these are of the same radius. I don't think I mentioned that at the beginning, but yeah. And then the area of the sphere, so subscript S, this is going to be 4 pi r squared. So this is just, pi r, I put an r2, I meant r squared. It's just a known fact, if you remember that about spheres. So yeah, 4 pi r squared, which means that there is 4 times as much surface area, this is surface area, there's 4 times as much surface area on the sphere, on the boundary of the sphere, than there's area on the circle. Which means that there's 4 times more room, and that things are going to be 4 times more spread apart. So this distance is in fact just 4L. Is that the end of the video? Are we done? Well, not really. Because now, remember how I said that we're not actually considering the inside of the circle, of the sphere, I mean. But what if we do? What if we decide to see what this, I'm going to draw like a dotted line here, or I guess it's not really dotted, but whatever. I want to see what that actual distance is along a straight line. And it might be weird because I said, okay, well the domain is the codomain is actually just the boundary. But now we're going to focus on like a different function other than f, and kind of think of what this mapping would be to that direct distance. So let's figure that out. So I'm going to draw a slice of the circle, of the sphere, I mean. I keep messing that up. I'm going to take a slice of the sphere along, and we're going to take like a plane. So I'm not going to draw the plane, but I'm going to basically take a plane and just slice it through such that it goes through these 2 points as well as the center of the sphere. And basically, once I draw a plane, that's just going to be a 2D thing. And what we're going to have is we're going to have, the center there, and then if I kind of just draw it similar to how the drawing is, let's say f of c2 is there, and then f of c1 is here. Actually, let me make this bigger, because I'm probably going to be drawing on this a lot. So there's f of c2, and here's f of c1, and so that's close enough. So we said that this distance is 4L, okay? Now that's not a perfect curve or whatever, how it's supposed to be, but it's good enough. And then this, let me make that straighter. This is just the radius, distance to the center, and so is that. Let me just make that a little nicer. Alright, whatever. This is good enough. So yeah, these are both the radii. And so what I want to know is that distance there, okay? And I'm just going to call that capital L. So I'm just going to call this capital L. That's the whole distance. And so yeah, let's just try to figure that out. So the first thing we might want to do is label this angle theta. Because now what we can do is we can do stuff with arcs. Arc length, because we have theta, r, and 4L. The only thing we don't know is theta, and we can very easily figure that out, because remember from geometry class, arc length is equal to radius times the angle. So in this case, arc length is 4L, and that's equal to r theta. That's easy. We can now conclude that theta is 4L divided by r. Alright, that's easy. So now, let me get the theta out of the way, because what I'm going to do is I'm going to bisect this arc, just so that we can split this into two right triangles. That is not a bisection. Here, let me make this better. Okay, that looks a little better. I'm not really good with drawing pictures, as you might tell, but, you know, it is what it is. So this angle is going to be theta over 2, and so is this angle, theta over 2, okay? And theta over 2 is just 2L over r, alright? So now, now that we have two right angles here, we can consider, so then this would also be L over 2. So this is L over 2, and so is this capital L over 2. Don't confuse this lowercase l with the capital L. But yeah, so it's capital L over 2 for both of those. So now we have this angle, which we know exactly what it is. We have the radius, which is the hypotenuse of this triangle, and we also have this opposite side. So it makes sense to just go with sine. So sine of theta over 2, which in this case is 2L over r, so 2 lowercase l over r, is equal to opposite over hypotenuse. So that is going to be L over 2 divided by r, or we can just write it as capital L over 2r. Okay, and so now what we really want to find is capital L. But I want to show first that capital L over 2, what that is. So capital L over 2 is r times sine of 2 times lowercase l over r. Okay, so this is just this portion, and if we want to find what the whole thing is, which is exactly what we wanted to do, that would be 2r times sine of 2 lowercase l over r. And that's exactly what we wanted. So we found that the direct distance, the straight line distance between f of c1, which I can write down, this is f of c1, and f of c2, that direct straight line distance is 2 times the radius times sine of 2l, which is that, divided by r. Okay? And if we want, we can write this in a little more straightforward notation. So I'm writing it in absolute value bars, but you can think of these as vectors, because c1 and c2 are both coordinates, and in fact, f of c1 and f of c2 are three-dimensional coordinates, so you have to consider those as well. So this is 2r sine of 2 times c, let me write it this way, C2 over R times C1, or C2 minus C1. Just flip these around, just like that. And so yeah, this is another way to write it, but just remember that this isn't totally absolute value, this is the magnitude. So you can, some people write with like 2 absolute value bars on each side, but I don't really like that notation. But yeah, so yeah, you can think of these as vectors. If you don't know what vectors are, that's fine. Just they're coordinate pairs. Here it's actually a coordinate pair. Here it's a coordinate triple. So yeah, you just have to make that consideration. So it's kind of difficult to calculate all this because you have to do a lot of different coordinate stuff. But this formula is actually not that difficult. It's a pretty simple formula, just involving sine and a little bit of other stuff. Let's just consider a special case where r equals 1, just where we're considering the unit circle and the unit sphere. So L is just going to be 2 sine of 2 times lowercase l. That's pretty basic. So yeah, it's just the distance multiplied by 2. Take the sine of that, and then multiply that by 2, and we get the total distance. So yeah, thank you guys so much for watching, and I'll see you in the next video. Bye guys.